All right, let's go ahead and get started. I'll adjust the lights. As you can see, the projector's working. They replaced the lamp. Life is good today. Hi, everybody. How are you all doing today? Did you all get your algorithm design in on time? Are you happy with it? Programming is going to be easy now, right? Because you've already done the algorithm part, so the programming part's going to be, yeah. All right, I don't see a lot of conviction. It'll be easier after you've done it like once or 2,000 times, somewhere in there, okay? It'll get easier as you go along. So let's just review what we've done over the course of the semester. Last times in the past, we talked about algorithms. What's an algorithm? An ordered series of steps used to accomplish some task. We have a program which is working on next week, which is? Yes, is correct. Yes, I heard many of the right words in there. An algorithm expressed in a form a computer can execute and humans can understand. So we went through algorithm development. We talked about how we outline our algorithms, and you've just done that, so you should be getting good at that. We've talked about program development, and you've done the second homework on editing, compiling, doing some bug catching probably in there. We've talked about how to do comments. We talked about C++ comments and C-style comments. We talked about basic data types, bool, character, float, int, and we'll talk some more about those today. In fact, let's do it right now. Bool, what is a bool variable? True or false. And last time we talked about the specific words true and false. And they have a specific meaning in C++, and you cannot use them for other things like variable names. What is true? What is false? Sort of. Here's the deal. The way the computer actually represents true and false inside memory is everything is a bunch of bits, right? Ones and zeros. Something is true if it is not 0, and something is false if and only if it is 0. So, given that there are quite a number of different ways to have things that are not 0, and only one way to have things that are 0, then there's a lot more truth in the world than false, okay? This is going to become important later, and I'll show you some situations where there are things that turn out not to be 0 that you wouldn't expect to be true, but are, okay? So, what is false? What is true? Is 1 not 0? So by default, if you use the word true, it puts 1 in there. But is 17 also not 0? So is 17 true or false? How about -1? How about the letter A? Okay, all of those things are not 0, so they are true. We talked about floats, right? What is a floating point? A decimal number, and it holds some value. What we haven't talked about is how floats work, okay? So let's talk about that briefly. And I'm just going to tell you right now, everything I'm about to tell you is a lie. I'm lying to you throughout the next 4 slides. But I'm lying to you in a way that will give you an understanding of what's going on without going into a lot of complexity about what's going on, okay? Are you all good with that? I'm going to close this door because it bothers me. Okay, so here's the deal. If we look back at how binary numbers are stored, we've seen this slide before, right? And what we did is we worked from right to left. We had 2 to the 0, which was the 1's place, the 2's place, 4's, 8, 16's, 32. This all seem familiar to you? And when we wanted to figure out the value of a binary number, we just took either 1 or 0, each one of these values, 1, 2, 4, 8, 16, 32, and we added them up and we got some number. Everybody good with this? Well, here's the deal. Decimal numbers conceptually work exactly the same way, except instead of dealing with positive powers of 2, we are actually dealing with negative powers of 2. What is 2 to the -1? I heard someone mutter it. 2 to the -1 is 1/2. When you start dealing with negative powers, as you probably remember from algebra, what is that, like 3rd grade these days, right? You use fractional values. So here we had 2 to the 0 before, right, which was 1. But now we're kind of extending this down to the negative number range. So we have 1/2, 1/4, an 1/8, a 16th, a 32nd, and I've represented the decimal values of those. So when you have a floating point number, just like before we had to calculate our integers as the sum of powers of 2, we calculate our fractions conceptually. Again, I'm lying to you. It's a little bit more complex than this. But we calculate our fraction as the sums of negative powers of 2. So let's say we wanted to represent the number 0.654 or something like that, right? I can't remember what example I used when I created this. But what ends up happening is the computer, when you give it a particular decimal number, does its best. It tries as hard as it can to come up with a sum of these fractions that adds up to what you want it to. More often than not, it fails. Okay? More often than not, it fails. Now, here we only have like 6 or 7 values, right? When the computer's working, it's actually working with 32 or 64, so the fractions get really small as we keep on going down. But what's going to end up happening is that depending on your decimal, you may not be able to represent it exactly, right? You may have a situation where the sum of all these little small parts cannot be made to add up exactly to what you want. Everybody with me on that? Does that make sense? So what that happens then is what you have is called representation error. Representation error, in that the sum of all these little fractions doesn't actually add up to what you want it to add up to. Does that make sense? Everybody with me? Now it gets a little bit worse because, you know, in this example I had on the previous slide, what I've shown you is just, you know, we have some bits just to represent the fractional part. But when we have a floating point number, are all our floating point numbers only the decimal part? They're not. We might have a floating point number that's like 65,873.29156. I have no idea what I just said. Don't ask me to repeat that. But you can imagine that if we have 32 bits, right, total to represent this, some portion of that will go to representing the larger part, in the integer part, the whole number part. Help me out, math majors, right? And some other part will go down to representing the decimal part. So if you're representing large numbers, large integer numbers that have a small decimal part, there may not be very many bits allocated to the decimal portion. And the reason it's more complex is that what happens is the computer kind of shifts around the number of bits that are being used for the integer part and the decimal part, right? So over time, you get errors in there. So everybody understand that? Okay. So we end up having this representation error where we may not have enough fractional pieces to add up to exactly the fraction we want. Now when we have representation errors, what ends up happening is if we do a lot of computation with decimal numbers, this representation error into time also turns into a rounding error. Because what will happen is, like, you'll take two numbers that have bad, not quite accurate representations, and you multiply them together or divide or something, and the result will itself will end up being rounded, right? It'll be fit into some number representation. So the errors accumulate over time. The more operations you do, the less accurate your floating point numbers really become. Okay, sorry I had to turn up the thing a little, the sound level isn't right. So here's what happens over time is that you accumulate this kind of this little error in your end of your decimal numbers, and the more operations you do, the more this error accumulates. And when I was in graduate school, I took an entire semester-long course in an area called numerical analysis that was all about how to figure out when you were doing math how accurate your result was. So there's a huge field of study just on dealing with floating point numbers. But let me tell you the some thing that you need to know today. Right now, the one shocking secret that causes problems for you, and is that when you use this equal sign, you cannot guarantee the equality of floating point numbers. If you take two mathematical operations involving decimals, and no matter, I'm trying to think of an example of this, you go through two different calculations that should, in your mind, result in exactly the same answer. If they're floating point, equal may not work. It may not work, okay? The reason it may not work is because of this representation error that gets put into rounding error over the time, over the large number of calculations you do. So floating point numbers, when you use them, are dangerous. And they're dangerous because you cannot trust equal to work. What ends up happening is that the results might be the same, but like 20 decimal places out, you have one little fraction that's hanging out that's a little bit different, just because this rounding and representation error accumulated, and things won't be equal. Which leads us to this comic, which I found very amusing, and I'm hoping you'll laugh just to humor me. And it's a test to see whether it's the introduction to the secret robot internet. So you know how this thing, prove you're a human, right? What is 0.1 plus 0.2? To robots, it's actually 0.300000004. So, all right, and this will be funnier as you do more computer science because you'll see things like this happen. And I'll tell you, back in the day, like one of the original Intel Pentium processors, I can't remember which one because I'm old now, had an error in there where if you went into Windows and you added 2 plus 2 in the Windows calculator, you would get, I think it was like 1.999999997 or something like that, because the computer couldn't represent 2 accurately. This was considered a problem, and they eventually fixed it in hardware, but they had to fix it in the operating system first. Okay, so the question often comes up, which people ask naturally, is like, if you have problems with things, why don't we just use floating point numbers all the time? This is the reason why. Because floating point numbers turn out to be evil because they have these little decimals hanging out in the end. Okay? You can't trust them to be equal to each other. Yes? Mm-hmm. So when you do static casting to convert something, what it actually does is it converts it just for that. It makes a copy of it conceptually and then just uses that copy for the operation and throws it away. Okay. And it has to do with how the CPU actually stores numbers internally, if that makes sense, but we're not going to get into that. So, okay, so everybody good? What do you use floating numbers for? For decimal, but you don't ever trust them to be equal to each other. Yes? Yeah, the representation error is when you have this problem where a number is the sum of a bunch of fractions, and you don't have the right fractions to represent the number you want exactly. Okay? So let's say we were trying to represent, 0.65, gosh, I don't remember what number I had in mind here, 652 or something. It could be that if you're trying to represent 0.652, I think maybe 655 is what I was going for, right? The closest you can get to 0.655 using this is 0.65625. Okay, does that make sense? And so the number that's represented in memory is not the same as the one that you thought it should be. Everybody good on these? All right, so don't trust floating point numbers to be equal to each other because of this. They're useful for doing calculations, but it's very difficult or impossible to compare them. All right, so we've talked about int, int, bool, float. What are we missing? Char. What is char? What type is that? It's a character. It's a single letter. Now the question is, we know that everything in there is just a bunch of ones and zeros, right? The ones and zeros are interpreted differently depending on what type they are. So if we're a character, the question is, how do we represent letters using a bunch of ones and zeros? And the answer, which I flashed up on the slide earlier for those who are fast, was you have a numeric code for each letter. Okay? Each letter on the screen has a code behind it. And let's take a look at these for a second. Most of the time what we use and what shows up on our machines, I think by default these days, is something called ASCII, A-S-C-I-I. ASCII code has been around probably longer than any of us in this room. It goes back to the days of teletypewriters. And this is a table that shows the ASCII codes. ASCII codes range from 0, I'm looking at the decimal column here, all the way up to 127. They are 7 bits. ASCII codes are 7 bits. And back in the day, what would happen is when you logged into a computer and connected to a computer, you wouldn't have a monitor. You would have a keyboard and this big pile of paper that rolled through the thing that looked like a typewriter. and you would press keys, and the keys that you pressed would be sent over the wire to the computer, which would interpret as an ASCII code and then send a code back, and it would print that code on this big unfolding piece of paper. So what we have is we have a whole bunch of these like weird codes. This first column, no, STX, ACK, BEL, all of these things are codes that are left over back from the early days of computing. We don't really use them that much these days, all right? But what we do have is we have all these other characters and letters. So, for example, space at the top of this column is 32, exclamation is 33, 0 is at 48, uppercase A is at 65, lowercase a is at 61. Okay? Now, I don't expect you to memorize these things. I used to remember those four because those were useful to me to figure out what was going on, but they're not useful to me anymore. I don't use it very much. But what ends up happening is each character is represented by one of these numbers. Now, we know that hex is the same thing as decimal. It's just a different way of representing things, right? So this chart shows you the decimal and the hex value as well. Now, the reason you might be asking, why am I showing you this? Because do you really care? How many of y'all care? Nobody cares, not right now. You'll care later. You'll care later when you have to compare two characters. Because if you want to see if two characters are equal, you can use equal, equal. And what it does is it compares the numerical value. But if you want to use something like greater than or less than, it starts to get weird. Because is 0 greater than or less than capital A? Less than, right? 0 has a decimal value of 48, capital A is 65. Is lowercase a greater than or less than capital A? Greater than. So when you start, if you ever compare characters using things like greater than or less than, what you're really comparing are these numerical codes that are behind them. Okay? And weird things will happen. Because why is 5 less than capital A? Why is at greater than right curly bracket? I don't know. It's just, that's the way it is. All right. Now I have a question for you. How many different languages around the world can you represent using this particular table? Pardon? A small handful, right? Because a lot of languages have additional characters. I speak a little Spanish, and we're missing like the N with the tilde over it and things like that. And you can imagine for the vast majority of other languages in the world that use an entirely different alphabet, this just doesn't work very well. So what's happened over the years is that people have kind of come to accept that ASCII has just an insufficient character set, an insufficient set of symbols for for many languages, and now people are moving to something else, from ASCII to something that's called UTF, which you don't even need to know this. U is Universal Character Set Translation Format. You'll see this abbreviated as UTF. Everybody calls it Unicode. Unicode. The idea of Unicode is that it has more than 7 bits to represent characters. In fact, it has a number of bits that varies depending on the language and how many letters you need. But essentially, there are like an infinite number of characters for this. So, and don't really mean infinite, but a huge number that way exceeds the number of different symbols we have in different languages. All right. All right. So that's what I wanted to show you last class when the projector wasn't working. Everybody feel they have a kind of idea of what's going on now with these different things? A lot of times nowadays, pretty much you'll use UTF. I believe our system is still using ASCII right now, just by default. You have to tell it to use UTF a little bit differently. All right, so there we are. Let's see what else we were working on. So last time we had talked about dividing numbers. All right, I'm going to turn on the light and give you all a break for a sec. Stand up, stretch. Anybody want to yell? Jump up and down. I just talked for like 20 minutes straight and nobody said anything except for like 2 people. And I'll say today I have exactly 3 caramels because I ate all the rest. And so you want to catch me in a mistake today, and you can win one of the prize 3 caramels for this class. And if, yes? So the question was, if I gave you a number on the exam for you to translate into decimal, you could do it, the binary representation. How would I do it if I gave you in decimal? I would not expect you to be able to do it in decimal. That's the honest answer. And in fact, if you gave me a number in decimal, I probably couldn't. I'm certain I couldn't do it without going up and looking up the spec. The storage of decimal numbers is actually really complex. And again, it's complex because the way it's encoded is there's a certain number of bits at the front that tell how many bits are like the integer part, and then there's a certain number of bits that are the decimal part. And then sometimes there's like an encoding that switches how those other encodings work. There's some very crafty things going on there. So. All right, I'll let you go back to sleep now. All right, so last time we were dividing two numbers. It was all very exciting. We got to the end, and because I was just having generally a bad day, I messed things up. And what we were trying to do, and what I was trying to introduce you to, was this idea that we can include libraries. The one we were talking about was what? Pound include all the answers. That would be nice, wouldn't it? All right. Pound include math.h. And there's different ways to do this. I think you can do CMath and stuff like that. Math.h works for me. And when we compile using this, okay, I just need to make it so I can switch back and forth easily. Okay, so when we compile using the math library, it gives us a whole bunch of additional functionality. And there's a bunch of things that math does, and I believe it's in the book. Book. I should mention, I posted on the webpage the readings up through like chapter 3. I haven't put a particular date on them, but they are the readings that match what we're doing in class. And they're pretty brief. The book is straightforward and terse, so I like it. Y'all liking this book? It's the first time I've used it. How many of y'all like it? How many of you don't? How many haven't looked at it yet? All right, well, you still have time to form an opinion. All right, so what we're going to do is we were going to try and make things round up, right? Make things round up. And the math library provides a number of different functions for things that we need to do. It's got stuff like square root, you know, all the different cosine, sine, arc cosine, tons of different things. And if you just search math.h on Google, you will find a whole list of all the different mathematical functions that it will provide for you. The one that we're interested in today is the one that does what? Rounds up. And what one was that called? Ceiling. Okay, so here's what we're going to do, is we are going to round up the quotient. When we talked about division, we knew that when we did this division sign that we would either divide using integer division or floating point division. How do we tell the two apart? Floating point division you know because I have a caramel for the person who answers. Ready? Go. What? Wait. How do you know? No, throw that back. Wait, how do you know what you're doing, whether it's integer, when you're doing division, how do you know whether you're doing integer division or floating point division? The type of the variables has to be? At least one of them is floating point, you do floating point division. Okay? So, and do you notice that I keep emphasizing this? Do you think I emphasize the things that are fun for me to emphasize or the things that are important? Okay, so it's important. So the reason we get floating point here is because we've taken x is an integer, we know that, and we are casting it to a float, so we get floating point division. Now, in our particular problem for our assignment, we want to be able to round things up, right? So we can round things up using the ceiling function. And the way we do this is we just write the function is called ceil, C-E-I-L, and we wrap this whole thing in parentheses. And we'll talk about exactly how this happens in just a few minutes, but essentially ceil, C-E-I-L, is the function that's included in the math library that rounds up floating point numbers. So let's try this and see if it works. It's the same code as last time. try not to overwrite the code, because that would stink. Oh, no way. I thought I had fixed this. All right, so here's what we're going to do. We'll work on CS class again. Sorry, I'm going to have to recreate the code really fast. All right. All right, so here we are back where we were. We have the same thing. I'll put ceiling around this, around the whole thing. And now we should be able to divide. Let's try it. Divide 2.cc.o divide 2. Okay, so it compiled cleanly. We're happy. And we run it. We say divide 2. And it says the result is 7 and the remainder is 1. Is that correct? Well, let's go back and look at what we were dividing. We were divided 43 by 7. What does that give us? 6 1/7, which is like 6.14 something. But it printed out 7. Why? Because it rounded up. Let's just make sure ceiling works like the way we expect it to. And what we'll do is we'll change this to 42. 42 divided by 7 should be, and is it going to round 6 up to 7? Why not? All right, so let's see what happens. Unless there's what? So it said 6, remainder 0. Okay, so let's try one more thing just for fun. Let's divide 42.5.